Today, we are modeling a realistic plate heat exchanger from scratch in AutoCAD Plant 3D. We'll route the piping, hook up all valves, and position the vents and drains. Along the way, I'll share real-world engineering challenges and mistakes I've faced when designing these systems in my career. Let's get straight into it. To start routing the piping, I first need a heat exchanger, obviously. Now, I could just draw a generic box and convert it into an equipment object, but instead, I wanted something that actually looks real. So, I grabbed this detailed model from GrabCAD. When sourcing equipment online, I always look for .step or .dwg files because I know AutoCAD Plant 3D handles them flawlessly. I intentionally avoided formats like SolidWorks or .dwx, as importing those usually requires a much more complex workaround for equipment. Now that we've imported this 3D solid, I'm going to block out a quick reference envelope around it. This lets us model the piping within its actual local environment, ensuring we are designing in context rather than just floating in empty space. I'm elevating the heat exchanger slightly above floor level to provide enough clearance and comfortable maintenance access for the drains and vents. Keep in mind that when you're designing the concrete foundation, you'll need to know both the operating weight of the unit and the exact anchor bolt locations. A concrete foundation with a 100 mm perimeter offset and a height of 200 mm will work perfectly for this load. I just drew a generic box and stretched it to size. However, when designing foundations, always keep your dimensions precise. In this case, 1000 by 500 by 200 millimeters. Here is a critical tip from real-world projects. Always double-check your inlet and outlet nozzle locations, as well as the hot and cold fluid sides. It's a lifesaver to clearly mark the hot and cold sides directly on your 3D model, so you always know exactly where the flows enter and exit. Next, let's measure the nozzle width to determine the exact pipe size we need. This is a crucial step when using anonymous models from GrabCAD. They look great, but they don't come with a spec sheet. In a real project, you would always pull official certified drawings and dimensions directly from the manufacturer. The measurement is around 100 millimeters, so I'll use a DN100 pipe to keep the scale realistic. Now, our next step is to convert this imported 3D solid into a native plant 3D equipment object and start adding the nozzles. Once converted, adding the nozzles is simple. You just define the direction and the start point, and then enter the details for the nozzle size and connection area. Pro tip from my own experience: sometimes the equipment geometry makes it really hard to snap to the exact start point. When that happens, just isolate the equipment object and rotate your view so you have clear, empty space behind the nozzle. It makes catching that insertion point so much easier. I'm setting the nozzle connections to plane here because in real-world industrial setups, these plate heat exchangers are very often connected using special clamps or quick connect couplings rather than standard flanges. While I'm adding these next two nozzles, take a look at how long these tie rods are. This back plate area must be kept completely clear. Periodically, the maintenance crew will need to unscrew these long bolts and slide the plate back to clean or replace the internal plates. If you route piping directly behind it, they won't have the physical room to service the unit. Now that our equipment is live and ready, let's start routing the pipes. And let's be honest, in this line of work, you rarely get it right on the first shot. Don't be discouraged if you have to rip it out and redo it 3 times before the layout feels clean and functional. The raw recording of this modeling session is actually 74 minutes long. To save your time, I've sped up the footage by 2x and cut out all the mistakes and dead air. You'll get straight to the point, high-value engineering workflow. When routing these lines, you always need to plan ahead for ergonomics and maintenance. Make sure every single valve is easily accessible and not buried behind other pipes. I also focus on maintaining a clean piping order. Avoid creating unnecessary loops or U-shaped lines. Those pockets trap fluid, cause airlocks, and make draining the system a nightmare. Keep your runs straight, logical, and clean. Another strict rule I follow: always keep your straight pipe runs to a minimum of 100 millimeters. For example, If you're dropping in a drain branch, you need to leave at least 100 millimeters of straight pipe on each side of the fitting. While routing, I'm constantly thinking about the welder on site. Your goal should always be to minimize the number of weld seams. Fewer seams mean less time on site, lower testing costs, and a much cleaner, safer pipeline. For this setup, we have 3 distinct process lines to route near the heat exchanger: the cold water utility, the hot water utility, and the actual product line that needs to be cooled. My plan here is to route all 3 lines overhead, directly above the heat exchanger. This keeps the floor space completely clear for foot traffic and safety, and creates a neat, organized overhead pipe rack that drops straight down into the equipment nozzles. When routing multiple lines next to each other, a good rule of thumb is to maintain a minimum of 100 millimeters clear distance between the pipe walls. You need enough physical space to comfortably fit your hand between the pipes for installation and maintenance. But here's the catch: always pay close attention to insulation thickness. Remember that valve insulation jackets and flange covers take up significantly more space than standard pipe insulation. If you don't account for that extra bulk during the 3D modeling phase, your pipes will clash on site before the insulation even goes on. Let's briefly touch on how a plate heat exchanger actually works. Inside this frame, we have a series of thin, corrugated metal plates packed tightly together. Channels are formed between these plates, and the gaskets direct our hot and cold fluids to flow through alternating channels. This layout gives us a massive surface area for heat transfer in a very tight footprint, making these units incredibly efficient compared to old-school shell and tube exchangers. Right now, all these routed lines are showing up in yellow, which can look a bit confusing and makes it hard to see which fluid flows where. Don't worry about that just yet. Once the layout is finalized, I'm going to set up the proper system color coding based on the fluids and their operating temperatures. It will instantly make the entire model clear and readable. Now, let's start adding the valves. We'll begin with the isolation valves on all 4 lines. I could easily use the generic valves from the standard AutoCAD library, but I want this model to look as realistic as possible. To get that high-end, professional finish, I went to 3dfindit.com and downloaded real-world manufacturer models. It takes an extra minute, but it makes a massive difference in the final 3D layout. I selected a manual, full-bore ball valve operated with an L-shaped lever, and now I'm converting it into a live plant 3D component to place on our lines. If you look closely at the first valve I dropped in, I noticed the model didn't include the lever geometry. To make sure the installation is completely practical and maintenance-friendly, I decided to switch it up and use a fully ended union connection here. It's a much cleaner choice for these compact lines. Before making the final connections, I always double-check the port properties to ensure everything generated accurately with the correct rating and size. Once that's verified, we can seamlessly attach the valves to the pipelines, and Plant 3D will automatically generate the corresponding weld seams and gaskets. Notice how I placed 2 of the valves lower down and the other 2 slightly higher up. This is a deliberate technique called staggering. By offsetting the valve positions, we prevent the wide flange assemblies and insulation jackets from crowding each other. It gives us maximum clearance between the lines and makes bolt tightening much easier on site. According to piping best practices, a valve lever should ideally point in the direction of the flow when open. However, real-world engineering is all about ergonomics. In tight layouts like this, I often rotate the valve or the lever to a more comfortable, practical position. At the end of the day, if the operator can't physically reach the valve to turn it, the theoretical flow alignment won't matter. Next up, we are adding the second component, a balancing valve, which I also grabbed from 3dfindit.com. You'll notice its distinct shape features small adjusting hand wheels right on the body. Its main purpose is to handle hydraulic balancing when you have multiple exchangers operating in parallel. Without these valves, fluid naturally takes the path of least resistance, starving some units while overloading others. By adding a balancing valve, we introduce controlled resistance, ensuring an equal, optimized flow to every single heat exchanger in the system. Now, I'm converting the balancing valve into a live model and dropping it directly into the outlet line, right underneath the isolation valve. In this specific project, we only have a single heat exchanger setup. However, I really wanted to include this component to highlight a critical engineering concept. Remember, you use a balancing valve whenever you need to balance the flow across several units standing in parallel. Showing it here prepares you for larger, real-world industrial layouts. The component I'm using here is a manual or static balancing valve. You lock it into position once during the plant commissioning phase. If your facility has highly dynamic loads where flow demands constantly shift, you would step up to an automatic or dynamic balancing valve, which adjusts itself on the fly to handle fluctuating system pressures. Now that the piping layout is complete, let's set up the system color coding to make the flows instantly clear. On the front side of the plate heat exchanger, we have our cooling utility lines, blue for the cold water inlet and red for the hot water outlet. On the rear side, we connect the process lines for the product we need to cool down, which I've color-coded in green and yellow. In 3D modeling, you must clearly reveal exactly where each coolant and product line connects. In my engineering practice, I've seen situations where lines were welded to the wrong nozzles on-site. Having to cut out finished piping and redo it from scratch is an incredibly frustrating and costly mistake. Doing your color coding right in the model prevents these disasters before they ever reach the field. Now let's talk about two small but absolutely critical details that separate amateur models from professional, high-end plant design: high point vents and low point drains. Now, at the absolute lowest point of the system, I'm preparing a 200 millimeter straight pipe run for the drainage branch. This length gives us a solid, clean drop to clear any surrounding insulation and ensures the drain valve is easily accessible. For this drainage branch, a DN25 line is going to be absolutely perfect. It's the industry standard size for drains like this, large enough to empty the system quickly without getting clogged by any debris or sediment, yet compact enough to keep our low point footprint clean and minimal. For this DN25 drainage line, I'm downloading a standard threaded ball valve. In utility and drain applications, you don't need heavy, expensive flanged equipment. A threaded valve is the ideal choice here. It's simple, cost-effective, and highly reliable. It screws directly onto our 200 millimeters pipe nipple, keeping the low point assembly lightweight and completely leak-proof. When converting this valve into a live component, I'm actually going to select plain ends instead of threaded ends. Here's a quick plant 3D tip. If you choose threaded ends in the software, AutoCAD often forces bulky box-type couplings onto the joints, which unnecessarily clutters the 3D space. By using plain ends, we keep the model clean and lightweight. Then, we simply specify in the valve's datasheet and catalog properties that this is a threaded component. It's a much smarter way to manage your project data without messing up your visuals. And there we go. Here is the final, realistic look of our threaded valve in place. Why do we need drains and vents? Well, when you fill the system with water, air gets trapped at the highest points, creating air pockets that block fluid flow and drastically reduce heat transfer efficiency. To fix this, you must place a vent valve at the absolute highest point of your piping run. On the flip side, whenever the plant needs maintenance, a shutdown or winterization, you have to completely empty the system. Fluid can't magically drain uphill, so you must install a drain valve at the absolute lowest point of the line. Skipping these means operators won't be able to safely service the equipment. Now, to save time and maintain absolute consistency across the project, we aren't going to build the second drainage assembly from scratch. Instead, we can simply copy this entire drainage branch over to the other side. But as is often the case with 3D routing, once you see the component in place, you realize it's not quite perfect yet. Engineering design is an iterative process. To finish off our drainage setup, I'm going to leave a clean, straight pipe run dropping directly down from the bottom. Let's get started on routing our vent piping. As you can see, These vent lines aren't placed at the absolute highest point of the entire system. Instead, they are strategically positioned right here near our heat exchanger isolation valves. While the general system air will naturally travel further down the line to the main manifold high points, these specific vents are designed to act locally. When we begin drawing lines and emptying the equipment, opening these valves allows the system to breathe, breaking the vacuum so the fluid drops out instantly. Just like we did with the drainage, we can save a lot of modeling time by copying this completed vent branch over to the other line. Once it's pasted, we just need to adjust it to fit the exact spacing and nozzle position on this side. While modeling these small branch lines, always think about the operator who will actually use them. Don't orient the valve handles in a way that forces someone to crawl under the main piping structure or struggle to reach them. Keep the handles facing outward toward the maintenance corridor or the open servicing side of the heat exchanger. To truly understand the scale of our heat exchanger unit, let's drop a 3D worker model right next to it. In industrial plant design, adding a human figure is a game changer for layout validation. Instantly, you get a realistic sense of proportions. Look at our valves and that straight vertical drop we just adjusted. Now we can clearly see that it sits at a perfect working height. The operator won't have to awkwardly bend down or struggle to reach the handle. It proves that our 3D layout isn't just correct on paper, but completely optimized for real-world maintenance. And that is how you design a clean, maintenance-friendly piping layout around a heat exchanger in AutoCAD Plant 3D. If you found these engineering tips helpful, make sure to hit that like button. Subscribe to the channel for more industrial design workflows. Thanks for watching, and I'll see you in the next one.